The first of our types of reactions is a combustion reaction. For our purposes, we're going to focus primarily on the combustion of hydrocarbons. Hydrocarbons are compounds that consist of hydrogen and carbon and maybe some oxygen mixed in. You're familiar with the concept of a combustion reaction. This is your classic burning reaction. We all know that burning takes a fuel, which is going to be in this case some kind of hydrocarbon, and some oxygen in order to get it to burn. The result of a combustion reaction is carbon dioxide, water vapor, heat, usually light. This is your classic flame reaction. Because of the intense heat, the water that's produced is going to be produced in the gaseous form. The general pattern for all of the combustion reactions is going to be a hydrocarbon plus oxygen gas yields carbon dioxide and water vapor. A more specific example of this is shown here, the combustion of ethanol. This would be the reaction that takes place in one of the little sterno burners that would fuel something like a fondue pot or would keep your food warm at a buffet. The ethanol, in its gaseous form, reacts with 3 oxygen molecules to produce 2 molecules of carbon dioxide and 3 water vapor molecules. One of the most important ideas here is that hydrogen gas is not a product. The only 2 products here are carbon dioxide and water vapor. The next type of reaction is the decomposition reaction. Decomposition is exactly what it sounds like. It's a process of something breaking down. In this case, one reactant is going to become more than one product. The general pattern here is a compound yields one product plus another product plus however many products your compound happens to break down into. A good example of this is the reaction of hydrogen peroxide decomposing to form water and oxygen. This is the reaction that takes place when you injure yourself. You pour hydrogen peroxide on the injury and it begins to fizz. The bubbles you see in that fizz are the oxygen gas, and the high concentrations of oxygen are able to kill the bacteria, and the bubbling removes some of the dirt from your injury. Probably the most important ideas here is that typically the products of a decomposition reaction are small, familiar molecules, and when you have to predict the products, just be aware of diatomic elements like oxygen and hydrogen when you write your chemical equations. The opposite of a decomposition reaction is a combination reaction. This is when 2 or more reactants combine to form a single product. Our general pattern here will be reactant 1 plus reactant 2 plus perhaps some others, all getting put together to make one product. An example of this would be the production of sodium chloride. Sodium metal can be melted and put in the presence of chlorine gas to produce 2 sodium chloride formula units. Notice that we have 2 elements here going together to form a compound. It's very important that when ionic compounds are formed, you handle the charges first as a priority and then go back and balance the equation. At this point, pause the video and see if you can figure out the products to this reaction and balance the equation. Remember to check the charge for strontium and the charge for nitride before you start so that you can make a good compound. Hopefully you came up with the answer. 3 strontiums plus an N2 gas yields an Sr3N2. The equation is balanced, but more importantly, notice that the strontiums and the nitrides got together in the proper ratio to make an ionic compound that doesn't have any charge. You may not have known what physical state to put on the product, but at this point in time, that's okay. Our next category of reaction is the single replacement reaction. This is when one element displaces another to form a compound. The general pattern here is a compound plus an element yields another compound plus another element. Essentially what happens is one element replaces another in a compound. Looking at our example, you'll notice that initially the iron is in a compound with chlorine, and then the magnesium and the iron switch places, so that on the product side of the equation, the magnesium is now in a compound with chlorine, and the iron is by itself. One of the most important ideas here is that not all reactions occur. You're going to learn about something called the activity series, which will tell you which reactions occur and which don't. The rule is going to be that the more active element, the one that's higher up on the charge, gets to be in the compound. We will practice more with this idea in class at when we meet later. We'll hit on the activity series of the halogens in class as well. The last type of reaction is a double replacement reaction. This is a situation where the positive ions switch places between two compounds. The general pattern here is a compound plus a compound yields a compound plus a compound, or a lot of people write this as AB plus CD yields AD plus CB. An example of this is the reaction of potassium iodide with lead nitrate. Notice that when you look at the potassium iodide, it consists of potassium ions and iodide ions. When you look at the lead nitrate, it consists of lead 2 positive ions and nitrate ions. In a double replacement reaction, we're simply going to trade places with the positive ions. So the potassium is going to become partners with the nitrate, and the lead is going to become partners with the iodide. When we trade partners, we do have to be aware of the charges. Notice that with potassium being +1 and nitrate being -1, they get together in a 1-to-1 ratio, but with lead being +2 and iodide being -1, they get together with 1 lead and 2 iodides. Much like before, we're going to set priority on making sure that the charges on each new compound total 0, and then afterwards we will balance the chemical equation. The next time we meet as a class, we'll spend a little bit more time practicing on double replacement reactions. For now, you just need to recognize them for what they are and not necessarily be able to predict the products.